Hello physics students. In this video, we're going to be performing another momentum conservation experiment. At this point, you should have already printed out these two sheets, both sheets of the document I included in the Google Stream. And yes, it says Momentum Lab 3, and the last one was Momentum Lab 1. So we are skipping Momentum Lab 2. So we're going straight from 1 to 3. No, this is not a mistake. You have the right lab sheets. Okay, so here's the setup, and here's the kind of collision we're going to do. In the last experiment, Momentum 1, car 1 came rolling into car 2, and then they stuck together because of Velcro and rolled together. So it was like a collision in which the cars stuck together. This time, what we're going to do differently is we're still going to have this car sitting here waiting to be struck, but this car is going to come in and it's going to bounce because of the spring on the end of this car. So basically it's going to look like this. And this car, the blue car, reversed directions upon impact, and this one went forward. So we're going to analyze again to see that momentum for the system is conserved. Pi equals Pf. Now, in order to determine momentum, we need the masses of the cars and the velocities of the cars because P equals mv. So the masses, easy enough. I've got an electronic balance here. I'll put this on here, and I see 256 grams, which again, it has to be converted to kilograms, 0.256 kilograms. And again, you're not writing that down. You're getting your own mass from the Google Stream. So the next car, I'll get its mass too, and it's 511. Again, I'll convert that to kilograms, 0.511 kgs. Okay, so you will fill in your data here as well for the masses of the two cars that you find in the Google Stream. Now, we got the masses taken care of. What we need to determine next are the velocities. And just like in the previous lab, when we did Momentum 1, we didn't use a motion detector, we used photo gates. We're going to do obviously the same thing because you could see the photo gates here set up. Now, I already set up the photo gates to act according to blocked, unblocked. And again, what that means is that there is, as I've said many times, an invisible beam that passes from through this plastic right here. And we just set it up so that this plastic strip triggers that photo gate by crossing that light beam. Now I'm going to use an index card so it's bigger and you could see kind of what a better visual is. So it's like a stopwatch, this photo gate, that'll start timing as soon as the beam is blocked by the plastic strip. Then it's passing through, passing through, passing through. It's still timing. And then as soon as the beam is reestablished, because the card comes out, it stops the stopwatch. So it starts here, stops there. Oh, starts here, stops there. So we're going to get a time, and the distance it corresponds to is the width of this, well, plastic strip. So that's the thing we have to do first, measure the distance that corresponds to the plastic strip. But here's a thing that's different in this lab. Because the cars don't stick together, they're always moving independently throughout the lab, we have two different plastic strips, one for this car, one for that car. So we've got to measure them both. So I will do that now as carefully as I can. And this is 1.61. Oops, I forgot to convert it to meters. Okay. 0.0161 meters. And then the other plastic strip, a lot of times they're the same size, but not always. We want to make sure. Okay, this one is 1.55, okay, or 1.57, I would say. So So what I've done, you'll see this later, is I've retrieved these, or you're going to retrieve these distances from the Google Stream, but this is the size of the first strip that applies to the blue car. And I put it in both places because it stays on the car throughout the experiment. So it applies for the velocity before and the velocity after. And then the second size of the second plastic strip I put for car 2, but I put it in both places before and after the collision. You might want to do that also to keep the data as meaningful and as organized as possible. All right, so we have the distances. Now what we need are the times. So let me reset this experiment. And what I'm going to want to do is have this car has to pass completely through this photo gate before it strikes the other car. So this is a pretty good position for the red car. And then it'll come back. So let me clear the data. And here's our experiment. Okay, so what I'm going to do is show you that again with a view of the calculator so you could see the data occurring in real time, and hopefully it'll make more sense that way. So now we're going to watch the data being collected by the calculator in real time. But that'll happen very fast. So before we do that, I want to first show you the data being collected kind of in a controlled fashion. I'm going to bring in car 1, the blue car, and it's going to go through this photo gate here before the collision. So you see it went through, and this photo gate registered a time of car 1 coming through before the impact. Then what will happen is it'll hit car 2 and send it into the forward direction. And you see that what happened is when car 2 went through the second photo gate, it generated its own time. And then car 1, the blue car, because of the impact, was forced to go in the reverse direction. And so once again, it passes through this photo gate right here, generating a second time for this photo gate. So that's what's going to happen step by step, but in a very fast sort of sequence when I push that car through and see the collision and data taken in real time. All right, so let me clear this data. Okay, so here we go. All right, so again, that car here generated that one time, whereas the blue car went through twice, generated those 2 times. So I'm going to jot those times down. Of course, you're going to get your own times from the Google Stream. So what I'm going to do is reconfigure the camera and now take you through the calculations. How do we take these numbers? These are times, they're seconds. How do we convert that to velocity? How do we then convert that to momentum? And then how do we show PI equals PF? Well, it's time to perform our calculations and show that PI equals PF for the system. Now, P, or momentum, is equal to mv. So we already have our 2 masses, so that's good, that's a start. Again, remember, you have your own masses from the Google Stream. Now, to get the velocities, we need distances and we need times. So far we have our distances. You got those, your own from the Google Stream, for the 2 plastic strips for car 1 and car 2, repeat numbers there. Now we need the times, okay, because you need distance and time to determine the velocity. But here's a challenge. We have 4 distances, but only 3 times. And somehow, from those 3 times, again, you have your own, but the 3 times that you were assigned, you'll be able to determine 4 velocities. Now, In order to do that, you've got to think back to the way the collision proceeded and some points about the calculations. So any place where you actually have to calculate something, you need 3 lines. Remember, I'm not going to say what those 3 lines are, but you have to show the calculations in a nice way in the Regents curriculum. If any velocity is 0, you may simply write 0 meters per second. You don't have to show a calculation. By the way, I'm not saying necessarily that any velocity is 0. I'm just saying if one was, you could write 0. You have to determine if, and if yes, which ones or which one was 0. Another thing, if a car's velocity is the same as a velocity you already calculated, you do not need to show a calculation again, just write the answer. Again, I'm not saying that any car has the same velocity as another one, but if that were to happen, just write the answer. And then, if a car reverses direction, you need to, and I left it off for you to decide how to factor that in, because remember, momentum depends on velocity. Both of them are vectors, which means direction matters. So if something happened to reverse direction, you have to factor that in mathematically somehow. Again, that's for you to figure out. And any calculation needs to be rounded to the hundredths place. Now, so these are the hints, but what I want to do is show you the collision again in slow motion to help guide your thinking. So let me reconfigure the camera to show you the collision again, slow motion. This is the system before the collision. You need to figure out the velocity of the blue car and the velocity of the red car before the impact from this view. This is the system after the collision. You need to figure out the velocity of the blue car and the velocity of the red car after the impact. So hopefully that helps you figure out how to take the 3 times you were assigned. Again, yours will be different. Take these 3 times and determine 4 velocities. Again, I'll put this here, your hints, on the screen, and I'll create a pause to allow you to figure that out. Okay, so at this point, you should have velocities filled in for all 4 boxes. The next thing you have to do is, in this space provided, calculate the initial momentum of the system. So you have the 2 masses. Oops. You have the 2 masses. Those were given. You just calculated the 4 velocities. Using one or more of these, calculate the momentum of the system before the impact. So I'll create a pause to allow you to do that. Okay, the next thing you have to do is answer question 5. It says, according to momentum conservation, what should the momentum of the system after the collision equal? Again, you're not calculating it. You're using something you already calculated possibly, or something you already know about the system, and you're just predicting. And again, a prediction doesn't mean like a shot out in the dark. You're just guessing. You're making a physics prediction based on what you already know about the system, the final momentum of the system. So go ahead and make that prediction now. Okay, so that is number 5. The next thing you're going to do right here is, after you've made your prediction, you're going to calculate the final momentum of the system. So it has something to do with all this data you already determined, these velocities, some of these velocities, and the masses. Calculate the final momentum of the system. Again, show all work means you follow the 3 steps and get a final answer for PF equals. Okay, so go ahead and make that calculation now. Okay, so next thing we move on here, it's the percent error between the two momentums. So this will be the accepted value, what we started with. And this will be like kind of like the experimental. Do a percent error between the two momentum, system momentum values right here. Okay, so you might have percent error equals and something. All right, now we have a couple questions, not the same kind of conclusion as in the last lab, but something more just about the internal workings of momentum being conserved. The question here is, did car 1, the blue car, so this is the blue car, gain or lose momentum? And then did car 2, which is the red car, gain or lose momentum as a result of this impact? So just write car 1 gained or lost, right? Car 2 gained or lost. Two sentences right here. Okay, moving on to the next and last question of the lab. It says, without doing any calculations, explain how you know the momentum gain of one car equals the momentum loss of the other car. And then it says, don't just state the reason, explain it. So in this lab and in all collisions, there's something that's true about the momentum of a system. State what that is. And so don't just state it. Go on to then explain how that principle or idea about what goes on in a collision implies that the momentum gain of one car equals the momentum loss of the other. Why does that principle then imply this statement? So go ahead and finish that, and I'll create a pause for you to allow you to answer that question. So that concludes our second momentum experiment called Momentum Lab 3. I hope you enjoyed the physics. I hope you enjoyed the analysis and the thinking. I know I did. So I will see you in the next physics video.